Good? Okay, so I want to welcome you to the Dean's Distinguished Lecture of today. Today we have Pramod Khargonekar, who is the AD for the Engineering Directorate at the National Science Foundation. And let me read you a little bit about his bio. Professor Pramod Khargonekar was appointed by the National Science Foundation to serve as the AD for the Directorate of Engineering in March 2013. In this position, he leads the Engineering Directorate with an annual budget of more than $890 million. That's a lot of grants. The Engineering Directorate invests in frontier engineering research and education, cultivates an innovation ecosystem, and develops the next generation of engineers. He is a member of the senior leadership team at NSF and thereby involved in setting priorities and policies at the National Science Foundation. He received his BTech degree in electrical engineering from IIT Bombay in 1977 and MS and PhD degrees in electrical engineering from the University of Florida in 1980 and 1981, respectively. Professor Khargonekar's research and teaching interests are centered in theory and applications of systems and control. His early work was on mathematical control theory, specifically focusing on robust control analysis and design. So without any further ado, I'll bring you Professor Khargonekar.
Buddy, is this on? Can you hear me? Great, thank you so much for that warm introduction, and I also thank Faryar for making this visit possible. I have known you for a very long time, and I'm glad to be here at UC Irvine. What I thought I'm going to do today is to share with you a perspective on engineering research, education, and innovation from my perch at the National Science Foundation. So the outline of the talk is I'll begin by a discussion of the context in which we do our work, some of the drivers and trends that we see, talk about NSF engineering budgets and priorities, discuss some of the education challenges that we see, talk about promise of innovation and what we are doing there. Then I speak a little bit about broader impacts, which I'm sure is near and dear to your hearts, and grand challenges, and then wrap it up with some conclusions, and hopefully we will have some time for Q&A. So I want to begin at the beginning, at the founding of the National Science Foundation. This is one of the best public policy documents ever written. It had huge impact leading to the founding of the National Science Foundation. Whenever Bush was Dean of Engineering at MIT, and he was also in Washington during Second World War, leading the science and technology enterprise for the president. And then at the end of the war, he was asked to submit a document describing how science and engineering research could help the nation in peacetime. And if you have never read it, it's available on our website. It's an absolutely amazing piece of work in that it has had this amazing impact on the federal science and engineering research policy. I have a quote from the book, and basically it sort of speaks to how investing in science and engineering research, basic research, would be a benefit to nation in terms of national security, in terms of economic growth, in terms of national health, and so on and so forth. So this idea that fundamental research, academic research, would benefit society is deeply embedded in the foundation's thinking. So ENG stands for Engineering Directorate. So that's the short form. And we think of our mission as being something very, very simple to explain. How do we take taxpayer dollars and invest it into the future of engineering research, engineering education, and innovation that will benefit society? So what's sort of the wisest set of investments? So we think of ourselves as investors into the future, and the problem at hand for my job is how do I make the wisest possible investments on behalf of the public so that they will benefit from what we invest in. There are lots of pictures in this one that showcase some of the recent things that have come out of engineering funded research. I'm just going to pick one of these. The picture to the right top is a drone that is fitted with all sorts of sensors and so forth, that is dealing with forest fire. So it's sort of sending out data and signals from forest fire to inform firefighters and defenders and so on and so forth with how to use that information. So just an example of NSF-funded research. Moving to the larger context and drivers, if you ask an average person on the street, what are they really worried about? I think without a doubt in my mind, they're worried about jobs. So they are worried about jobs that pay well for themselves and for generations to come in the future. So that leads to questions such as economic growth, because that's usually what it takes to create jobs, productivity growth, because that's what it takes to create increasing wages, competitiveness, because we live in a globalized world, and you want to do all this while being sustainable. So use natural resources such as water and air and all of these types of things, and have a sustainable civilization. So that's what would be one of the major drivers or context for our work. We confront these really huge challenges as you look to the future. So if you look to 2050 with 9 billion people on this planet and 420 million people in United States, we are going to face major problems of all kinds, starting with food, with aging population, health, energy, which is what is needed for quality of life as well as for economic growth. Water, I'm standing in California. I don't need to talk to you about water. So I'll just skip past water. Security, the security landscape has completely changed from even 15 years ago, where the threat has become much more diffuse and challenges that arise from that. Education remains a huge challenge. How do we educate tens and if not hundreds of millions of people at affordable costs? Infrastructure, huge challenge. So any one of these problems is probably $1 trillion or more problem, and many of them far exceed that. And that's going to require advances in science and engineering research along with other things to solve. We live in a globalized world. And I think, a best example would be take your iPhone and think about all the components that went into it and where they were manufactured, designed, assembled in China, and then it comes back and is distributed globally, and then services are sold on top of that iPhone, such as apps and iTunes and all sorts of things. So you sort of begin to see how all these things are completely fluid flow of components, of products, services, knowledge, and I would say equally importantly, people. People are sort of constantly flowing through this global economy, carrying with them the knowledge and expertise. At the same time, coming back to sort of more US-centric issues, we face major challenges in terms of talent. So attracting people to STEM and to engineering from underrepresented groups, women, African Americans, Hispanics, Native Americans, and so on and so forth. So that remains a major problem for us. And very specific to NSF, federal funding for research. So making a case to the lawmakers and policymakers to give us the funding so that we can then in turn fund. So this is the sort of the big picture in which we think about our decisions and how we go about doing our business. Next, I'm going to talk about what we see as sort of the biggest drivers that is affecting the current and future of engineering research. Now, I want to make a little caveat here. I have taken an engineering directorate view of this. There is a sister directorate called SCIENCE Directorate, Computer Information Science and Engineering, and there is a huge parallel between the two, but you're going to hear a little bit more of an engineering-centric view of it. I think above and beyond anything, the ubiquitous computing communications is really just changing everything that we see in engineering. So it ranges from computational modeling, data, simulation, etc., to networks and computation deeply embedded in physical and engineered systems. And increasingly, the rise of machine intelligence, machine learning, which has tremendous impact on engineering and society at large. So that is like a huge force that we see changing everything. Second trend or second force that we see is systems, system science and engineering. We are doing multi-scale analysis and design and optimization, integrating physical and cyber components into these engineered systems. The range is enormous. We go in systems thinking all the way from nanotechnology, nanoscale systems, all the way to what I would call earth-scale systems. For example, the grid covers half the continent in the United States. And so any kind of an ecological system is an earth-scale system. So tremendous range of scales and complexity, literally tens, if not hundreds of millions of components. And if you go to Internet of Things or the grid, you're talking about billions and tens of billions of components working together in this large system. And so we want to worry about things like safety, robustness, and resilience. Nano has been a major driver in terms of science and engineering. NSF has been investing in nanoscale science for 15 years or more. Tremendous progress has been made in tools and understanding at the molecular and atomic scales in all kinds of directions. Where we see things going is to go from passive components to active manufactured systems. So that's the kind of change we see. Fourth one, which I could have been second or third, is the whole biomedical frontier. There, sort of, one way to describe what we see is interaction of engineered systems and biology at all scales, ranging all the way from DNA inside the cells, to organs, to organisms, to our bodies, and to ecosystems. So engineering and biology is interfacing at all of these scales. I'll talk about engineering for neuroscience and brain. Synthetic biology is a major development that can have huge impact on the future of engineering. Huge impact of engineering on plants, food, agriculture. It's a major playground for engineering advances to impact the world. Advanced biomanufacturing, I'll come back and talk about that, so let me skip past that. And then the reverse, where we take inspiration from biology to create engineered systems is another direction. Fifth major force or trend that we see is the rise of social and behavioral and economic sciences. So we see increasingly that anything we do in engineering has to take into account behavior of people, as individuals, as organizations, as societies, in order to come up with good solutions. So sort of the most compelling examples come from infrastructure. So take any of infrastructure systems, whether it's transport, water, energy. Any engineered solution would have to take into account people's behavior. And I had many meetings this afternoon that I'm sure resonate with this thinking. So we see incorporation of fundamental knowledge from social, behavioral, and economic sciences into engineering systems as a big area. And finally, which is something really intrinsically engineering, is the whole area of design, synthesis, creativity, and aesthetic aspects of engineering. So this is the big picture. How we go about doing our work is we are organized into 3 disciplinary divisions: CBET, CMMI, and ECCS. These are your typical departments, such as chemical engineering, biological engineering, and so on and so forth. CMMI is mechanical engineering, manufacturing, systems, and ECCS is all things electrical, computer, cyber. Then we have 3 cross-cutting activities. EEC is where our ERC program is housed, but also all our education investments come out of EEC. All the workforce investments come out of EEC. IIP is our industrial partnerships, academic partnerships, and small business. A factoid, in case you didn't know, the SBIR program was started by NSF. almost 45 years ago. Started as a $2 million program. Purest of pure science agencies said we need to invest in small businesses that are doing research-oriented work. And now it's a $2 or $3 billion program, which is adopted by all federal agencies. So that's housed in our IIP. We do all of SBIR for all of NSF. Engineering does all of SBIR for NSF. And then FRE is our Emerging Frontiers program, where we invest in new areas that are not yet part of any of the divisions. A little bit about our budget. I've taken this back to 2007, where we were just a little over $600 million. FY15, which is where we are right now, we are at $892 million. Our FY16 request, that is President's request for NSF engineering for FY16 is $950 million. So we are now very, very close to the 2009 peak, that extra dollars was because of the stimulus program. But if you take that out, there is a fairly steady trend of increase. So one message I want to convey is that, we hear all sorts of bad, very pessimistic thinking about our budgets. The reality is a little better than that. So, we are going to be close to $1 billion directorate in the near future. I mean, I hope it happens on my watch, but it's certainly, it's very visible that we are going to get there soon. Having said that, we could certainly, use more money, because we leave a lot of very good science and engineering on the table. So I have often said that Congress, we do what Congress tells us to do. So this is the money Congress gives us. But if Congress were to see, would to even double our budget, we would be sure to spend every single penny on worthwhile engineering research projects. So we leave a lot of very good stuff on the table because we don't have enough money. But it is going up. And this is a chart that I'm sure you would all want to see, our funding rate and number of proposals. So we are close to 10,000 proposals. And our funding rate is in the neighborhood of 17%. So it fluctuates a little bit, but it's in the neighborhood of 17%. This is an interesting chart, especially for junior faculty. 1 in 4 grants goes to somebody who has never had NSF money before. So we are very open to new investigators, very open to new investigators. I'll talk a little bit about our priorities. I'm going to now go over a bunch of areas relatively quickly to showcase for you where our priorities are. But I should say that I'm going to leave out 70% or more of my portfolio because that's in our core programs. So we continue to do our core programs through CBET, CMMI, and ECCS. And I'm just going to kind of pick on the highlights that are being emphasized. Instead of reading through this, I'm going to pick on these. So let me just sort of go to the next slide and talk about advanced manufacturing. Advanced manufacturing is arguably the #1 priority as far as engineering directorate is concerned from the president. So president is deeply committed to advanced manufacturing. This is one area that enjoys bipartisan support. So both sides of the aisle in Congress love advanced manufacturing. In every budget request, they tell us, spend whatever you are asking for in advanced manufacturing. This is an area that they want to see prosper. I thought it would be useful for us to know what is advanced manufacturing, because this term is loosely used. PCAST had a report on advanced manufacturing that gave a very, very nice definition of advanced manufacturing. So it's one of two things. One, it's either use or leverage of all things cyber. So information, automation, computation, software, sensing, and networking in manufacturing, or making use of cutting-edge materials and emerging capabilities coming out of nano, bio, chemistry, and so on and so forth. So it's either this leveraging cyber or leveraging new capabilities coming out of fundamental nanotechnology, chemistry, and materials and things like that. So, and it can be applied to existing products or completely new products. So this is what the sort of the big picture of advanced manufacturing, and this is what we support big time out of engineering directorate. A few areas that are getting special emphasis is nano manufacturing. So as I mentioned, NSF has been funding nanotechnology for 15, 16 years. We are very much emphasizing now moving this nanotechnology towards manufacturable products. So scalable nano manufacturing is a major initiative for us, investing in that. Basically, how do we go from materials and device advances to full systems that can be manufactured at reasonable cost? So that related to this is Materials Genome Initiative. The idea here is any new material from the time it is discovered to the time it's put in practice is 20 years or more, and it takes enormous amount of money. So MGI is a cross-agency initiative to cut down this cycle time and the cost. NSF, so this covers DOD, NSF, DOE, all other agencies are involved. NSF play in this is, can we cut down the time by a factor of 2? So how are we going to do this is through sort of 4 pillars. First is to do a culture shift in materials research to have a team approach that links computation, data, experiment, and iteration between these. Integration of experiment, computation, and theory, and very rapidly go through materials innovation process. Third leg is open data. So we want to encourage people to share databases on their materials and experiments and measurements. And finally, education and workforce. Our DEMREF program is directly aimed at supporting the Materials Genome Initiative. Third area in advanced manufacturing is bio. So here the idea is to encourage community to leverage biological systems of biomolecules, cells, and biomaterials to generate either new devices and constructs or to manufacture things like high value added chemicals and pharmaceuticals and so forth. So a couple of examples of what we are trying to do. A really new thing that we just put out on the street is cellular biomanufacturing. So NSF version for call for proposal is what is called a dear colleague letter. This is our way of saying we are open for business, send us your proposals. So here what we are trying to encourage the communities to come to us with new proposals that will put forward new concepts in manufacturing of cells, because cell-based therapies are likely to be a major new piece of personalized medicine. So already, I don't know if you follow cancer immunotherapy. So this is like a big new approach that is being tried to beat cancer using our immune system. And so if that's successful, and a lot of companies are heading in that direction with very promising results, we are going to have to manufacture these cells with high quality and repeatability and so forth in a personalized manner. So this initiative is sort of getting ahead of the curve and saying, okay, send us your proposal on cellular biomanufacturing. And we have identified some areas like novel cell expansion, differentiation, characterization, monitoring, and separation, and reproduce and reliable cellular processes. So quality control and so on and so forth is something we are seeking to. The fourth topic that we are emphasizing is this all things cyber being integrated into manufacturing. So one of the questions that we ask and we want to ask the communities is, what will factories of the future look like? What will a manufacturing plant look like in 2030 or 15, 20 years from now? So I just picked out a quote from McKinsey that talks about how Internet of Things is going to revolutionize manufacturing. We are very interested in seeding research to make this future possible. So we have a joint collaboration between engineering and computer science called Cyber Manufacturing. So how will continuing advances in network, software, modeling, simulation, and materials transform factories of the future? So come up with visions of factories of the future and show us how these things could be integrated to make that possible. And we really are hoping to have some breakthrough ideas that will make manufacturing much more agile and break down this like big, hard hardware, software packages that are needed in current day manufacturing into a much more flexible, almost app-based approach to manufacturing. CyberPhysical Systems is a big priority for us. This is the area where we integrate sensing, control, computation, communications into physical devices. And this is, again, a collaboration between engineering and science, and it's actually multi-agency. So NIH is a part of it, USDA is a part of it, many other agencies are, and engineering plays a big role in cyber-physical systems. NRI, National Robotics Initiative, is another big initiative that we are supporting. Multi-agency, again, engineering, computer science, social behavioral sciences, NASA, NIH, USDA, and in 2015, we're going to have DARPA and DoD also participate. And it's one single call for proposals where all these agencies. The big theme that we are pushing in NRI is co-robotics. That is, how can we get humans and robots to work together as co-workers, co-inhabitants, co-explorers, co-defenders. So go away from the era when robots were sort of behind safety curtains and so forth, and make them very much part of our life. And I know there is a lot of work going on at UCI in this direction. So big data, that's a big play for Science Directorate. In engineering, what we are encouraging is dynamic data. So what are the big data problems and questions and tools as we get this massive streams of data from online sensors that are distributed all over in the environment or on the factory floor or wherever. They're going to produce lots and lots of data. So large-scale distributed computing for dynamic data. This is a collaboration with Air Force. And we just started the first year. We are going to do another year next year and possibly beyond. Moving away from manufacturing and CPS and NRI, I want to talk a little bit about 2D materials. So graphene, as you know, was a big breakthrough which went from discovery to Nobel Prize to hundreds of thousands of papers in a remarkably short period of time. EU is spending $1 billion in graphene. So we decided at NSF that we would do something a little different, not duplicate what other agencies are doing. So we have identified this area of 2D materials. These are essentially sheets of materials, 2D structured nano layers. And they have all the properties of graphene, but have a lot more capability. So like they can have band gap, and they have great thermal properties or electronic properties or material properties. So we are in the second round of supporting 2D materials. These are just some examples for you to see in terms of 3D semiconductors or MOS2 based 2D layered materials. There are 3 themes: exploration of materials, properties, and device applications. Second theme is synthesis and nano manufacturing. And third theme is theory and modeling. And one of the requirements in our To-Dare program is that you must do 2 of the 3. That is, you won't get funding if you just did 1 of the 3. Because one of the things we want to do with To-Dare is to deal with manufacturing and synthesis right when we are doing materials and devices. We don't want to wait and find out that this stuff can't be made. So we want to invest in manufacturing. A second set of awards will be made this year. Moving towards BRAIN initiative, this happened in 2013. It was, I think, just within a month of my taking this job. So it was really a great timing for me that I got there just before this started. President announced a new initiative in neuroscience called the BRAIN initiative, and I've kind of put some quotes that he had. The BRAIN initiative will change that by giving scientists the tools they need to get a dynamic picture of the brain in action and better understand how we think and how we learn and how we remember. So the basic thesis behind the BRAIN initiative is to develop new innovative, so it stands for innovative technologies, neurotechnologies, is to develop tools that can measure tens of thousands of neurons in real time simultaneously. So sort of it's a big challenge, and Engineering Directorate is very much supporting this initiative along with other directorates at NSF. So what are the opportunities is there is a dear colleague letter for one or more IUCRCs in the BRAIN initiative. And then we have a new solicitation called Integrative Strategies for Understanding Neural and Cognitive Systems. And the emphasis here is to bridge scales. So both temporal scales as well as spatial scales, levels of abstraction, levels of analysis. And it involves engineering, science, education, human resources, and social and behavioral and economic sciences, because they do a lot of the work in terms of human behavior. Infrastructure systems remains a significant priority for engineering directorate. So, we have had historically a lot of investment in infrastructure. So, for example, all our research in earthquake and of great interest to California has been funded out of engineering. NICE facility, the whole NICE initiative was funded out of engineering. And then integration of engineering and social sciences. I mean, I had some meetings this afternoon where there is real resonance on how the two things need to be connected. As we move forward, we are heading towards multi-hazard approaches, so not just earthquakes, but earthquakes and windstorms or hurricanes or what have you. A major new thing that we are pushing forward, and I think, let me see what my next is. So let me just sort of say it here. One thing that we see is sort of absolutely game-changing is to rethink infrastructure. How so? So instead of thinking of infrastructure as hard physical goods, like if you think of transport, what do you think of? Well, I think of a car, I think of road, I think of traffic lights, I think of a gas station. But really, all of that doesn't really matter, because what I really care about is getting from point A to point B with some performance guarantees. So I want to leave my home at 7:35 plus minus 2 minutes and get to my office at 8 o'clock plus minus 2 minutes. So turn this whole set of physical infrastructure into service provision. So can we provide service to people with performance guarantees? This mind shift is very much possible because of infusion of sensors, networks, computation, and so on and so forth into the infrastructure system. So we want to encourage a mind shift. So if you think about Uber is the first little inkling of what can happen to infrastructure if you start to think of it as a service rather than a bunch of physical goods. And so we think that there's a lot more to come here than we have seen. We are interested in interdependency of existing and emerging infrastructures. So one of our initiatives in this area is CRISP, improving the resilience, interoperation, and performance of critical infrastructure such as water, energy, transport, and so on and so forth. Picture to the right is some simulation of earthquake in Salt Lake City, which could be used. So this kind of models could be used to help people deal with after effects of an earthquake. So resilience, idea of resilience. Again, I had a lot of meetings today that talked about resilience, so very much aligned with this way of thinking. I know there are a lot of people here who have received funding from SEAS program. So SEAS program is sort of coming to an end in a couple of years. We are thinking now as to what happens in the space out in the future, and this is our first step. It's called Infuse, Innovations at the Nexus of Food, Energy, and Water Systems. Again, I don't think I could have found a better place to talk about this than UC Irvine. Here is the thesis behind this program. The world population is going to 9 billion people, US to 420 million. Because of climate change, there is going to be much more variation in rainfall. Food, energy, and water systems have been traditionally thought of as three independent systems. So you grow your food, you provide your electricity or energy, and then you have water for our life. We think that these three systems are going to be increasingly interconnected and are going to collide, which is already happening. So again, California is ground zero for this collision because you've got agriculture here, you've got water, and you've got food, you got energy. And excuse me? You don't have water, which. So we want to encourage community to to start thinking about how are we going to approach this interconnected system. So we are calling for models of this coupled system. So that's one major thrust under Infuse is modeling of this three-way coupled system at sort of regional scales. Second is create and advance engineering solutions for more efficient use of resources in this food, energy, water system. And then advance sustainability, safety, and security of food, energy, and water resources. So this is an FY16 request, but we already gotten a start in FY15. So we released a dear colleague letter on food, water, energy. We have got already 150 responses to that request, of which, so there were 150 to all of NSF, 50 in engineering, more than 50 in engineering. So more than a third was just in engineering, because I think engineering has a big play in this area. We are giving supplements, workshops, conferences, eagers. And we think that the FY15 work that is going to happen in the next few months, towards the end of this year, will get the community dialogue around this topic and define fundamental research issues that NSF would be investing in FY16 and beyond. So this is a multi-year initiative that we hope to be funding for several years to come. So this is one of the offshoots of SEAS. So you can think of this as like taking the knowledge from SEAS and now creating a new opportunity to go after this problem. That's kind of a snapshot of our priorities in engineering. I left out a lot of stuff, so if you didn't see your favorite program, it's because I don't have the time to talk about everything that we do. I want to move quickly to education and talk about those issues. This is probably very hard to see for you, so I'm going to make it simple. The top chart shows, this is the latest data from ASEE, number of degrees in engineering to women and men. Degrees to women has fluctuated between 20.3% in 2004, and it's down to 18.9% in 2012. It went as low as 17.8. More or less, staying flat or steady or slight decline is basically the sum total of that chart. African Americans hovering around between 4.5% to 5%, between 4 to 5%, really no progress. Hispanics has gone well. We have gone from 5.6% to almost 9%. So there has been significant increase in Hispanics. Faculty diversity varies dramatically by department. So at the low end, you have fields like my own, electrical and computer at 11%, mechanical, which is slightly worse at 11.5%. So I think we compete for the worst field. But you got other competitors like aerospace and nuclear and petroleum really low. And then you have fields like chemical and environmental and biomedical that do much better. Very interesting data on women faculty over time. So we have gone from 10.4% to 14.5%. So in a good 4-5% increase. African American, really no movement, not much movement. Asians have gone up, Hispanics have more or less stayed flat. So women, slight improvement, but really no improvement in African Americans and Hispanics. The most interesting number is with assistant professors. It's at 22, 23%. It's higher than our undergraduate student population is in the assistant professor rank. So the challenge to academic world is, can we tenure these women and get them promoted and so on and so forth. But still progress is very slow. So I just want to draw some conclusions, observations that we are having major trouble attracting more women and minorities into our field. There is more progress with respect to women at doctoral and junior faculty ranks. Mechanical, I don't know about UCI, but nationally, mechanical has become the largest major on most campuses. In many places, it exceeds psychology and economics, which are traditionally the big majors. Mechanical beats them. So that's good news and bad news. So good news is mechanical is the largest. Engineering enrollments are going up. Mechanical is getting a lot of that. And mechanical does some of the worst in terms of women and minorities. So it's sort of a mixed bag. Although I should say that there has been an increase in raw numbers. So the raw numbers have gone up, but not as percentages. So can engineering as a field and profession really have a great future with these kinds of problems? So that leads us to some questions as to what are the models for success? I mean, how are we going to change this situation? How does success at one institution, so like University of Washington in Seattle, does really well with women in computer science, amazingly well, large public university. Well, if Washington can do it, why can't every other public university do it? So how can we transfer success at one place into another? How do we scale? So we have success in sort of a local environment. Some group does really, really well with this, but the scaling doesn't happen. And what's the role of culture? Does engineering have a culture that is unattractive to women and other minorities? And how are we going to deal with this culture? So so the question we ask is, where will leadership and vision for change come from? And what might we do by working together on this really critical problem? So we have gotten a start on this. We put a solicitation on the street called PFE Red, Revolutionizing Engineering Departments. The main idea behind this one is scaling. We want scaling and transferability, and we want department level focus. We want department chairs to be PIs on this grant, because we want to sort of empower them to bring about this kind of change. We are in the process of making awards under this solicitation, but we expect this program to run for several more years to come. So we would love to see some change happen here. Broadening participation remains a major theme for the foundation and for engineering. So includes our FY16 initiative, and its goal is to mobilize the STEM research community to open us for greater success in bringing underrepresented minorities into science and engineering disciplines. Main takeaway on this initiative is that this is the beginning of a multi-year rethink on broadening participation. So we are really looking to energize. NSF spends close to anywhere between $500–600 million to $800 million in broadening participation. It's a large investment that NSF makes in this space. So this 15 million is really nothing. It's a drop in the bucket. And so don't let that mislead, because what we are thinking is that through this new initiative, we are going to somehow rechannel, re-envision, remorph. And a couple of points. One, we don't think that NSF alone can solve this problem. It's too big a problem for NSF alone to solve. So we're really looking at approaches that can bring different stakeholders together to solve this problem. So there is some very interesting work in social sciences on how do you scale social innovations. So if any solution to the problem is going to have some kind of a social innovation, and how do you scale it? So one approach is what is called collective impact, where you bring different stakeholders together to work together to advance this problem. If there is time, I can go into much more detail on this, but this is an area to watch in the future. Career remains a huge priority for us. Our budget calls typically for $50–55 million for career, but we always spend much more on this. So our award size has gone up to 500,000. After a long time, we made that increase from 400 to 500. We just announced 146 new awards, and there is a very nice book on our website called Class of 2015. You can go there and click on all our career awardees and see what they are doing. These are the best ideas coming from junior faculty across all fields of engineering. I want to move a little bit to innovation. What are we doing there? So much of NSF is really in fundamental research. So to the left of this diagram is where most of NSF sits. Engineering has a little bit of piece, such as our ERC program, the GOLI program, the PFI programs, IUCRCs, Eiko, and then we have SBIR. And then, of course, to the right is industry and investors and foundations. So we are trying to sort of bridge this valley of death with all these different programs. One of the things that we are very interested in is the service economy piece. So the short version of the story here is more than 80% of US economy is services. More than 80% is service employment. So most people in the United States are involved in the service economy, not in the manufacturing economy. Now, it doesn't mean that manufacturing is unimportant. Manufacturing is very important for tradable goods and global competitiveness, but this is where most people are. So one of the things that we in engineering are talking about is what's our role in service economy? Now, there are some major shifts going on. So Xerox, which was this box company that made copiers and printers, has become a document services company, and that has already happened for the last many years. But much more interesting was 2 years ago, Medtronic had a new CEO, and Medtronic said that their future was in health services. So instead of thinking of them as a pacemaker company, they were going to provide you lifelong cardiovascular services. iPhone is a great example of selling services on top of a manufactured product. So this distinction between manufactured products and services is really going away, and it's much more integration. So we had an initiative under our IIP portfolio on smart service systems. So we are calling for platform technologies that can increase quality, efficiency, productivity of service sector. Eiko is really our major signature new investment in the innovation space. So this is an experiential learning program. Let me just use this slide, where we teach students, faculty, and third-party mentors on what it takes to take an idea from invention to the real world. By every account, I think there are 3 Eiko awardees at UCI at least, or more. It's a transformational experience. People who go through it come out of it saying, I will never do my research the same way again. I will rethink the formulation of my research project. Our goal at NSF is to build this Eiko to a national network. We have had 500 Eiko teams go through this program already. More than 45% have started new companies. Lots of companies have been bought out already. And so tremendous success and tremendous interest in this. There are 37 Eiko sites that we have funded now and 7 Eiko nodes. We are now scaling Eiko to other federal agencies. So there is now Eiko at NIH, there is Eiko at ARPA-E, there is something called LabCore, which is Eiko that national labs have created. And so we just continue to expand Eiko to other federal agencies. And ultimately, I see Eiko spreading to states and local and regional economies. So there is no reason why Eiko education should not be available to anybody who wants it and is ready for it, because everybody can benefit from this education. So ultimately, that's the kind of future we want to bring about, and we are making investments to make it happen. I'm going to now close with discussion of a couple of things. First is broader impacts. So as you know, NSF divided the 2 criteria into intellectual merit and broader impacts. Broader impacts encompasses the potential to benefit society and contribute to achievement of specific desired societal outcomes. What we are emphasizing is that in broader impact space, we need to have an institutional approach. So the story is relatively straightforward. Every institution, every research university takes great pride and invests a lot of money in having state-of-the-art equipment, research spaces, facilities that allow their faculty to do the greatest research and be competitive nationally. That speaks to the intellectual merit part of the merit review criterion. We feel that institutions have an important role to play also for broader impacts. So the National Science Board, in its report, called out that just as institutions play an important role in facilitating research-related activities, such a role can extend to activities directed toward the broader impacts of the project as well. So if there was an institutional framing, and there is a report called Perspectives on Broader Impacts that you can download from our website that talks about an institutional framework and an institutional approach. I'm going to send Faryar my larger PowerPoint presentation on this topic, so I'm going to cut this short. But basically, in my opinion, this is the new way to using facilitation, leveraging, and alignment to redo broader impacts in a much more powerful way than we have done so far. Grant challenges are really a very attractive way to talk about the work of engineering and bring new talent into engineering. So as you know, National Academies has articulated grand challenges in different parts of engineering. I think we can go beyond. So if you ask me what is the best example of a grand challenge, I would say it's President Kennedy saying, we will send a moon to the man and bring him back before the end of the decade. What were the characteristics? It was an inspiring goal. I mean, it inspired a whole generation of people. It captivates imagination. It was very ambitious, but not completely pie in the sky. I mean, one could imagine doing it. So it was ambitious but achievable. It was very specific. It put a timeline. It said end of the decade, and it had a very clear success criterion. A man has to land on the moon and come back, and that was success. So beautiful example of a grand challenge that can motivate, you know, tens of thousands of minds, if not more. And so I feel that engineering research community can use the grand challenge vehicle to really inspire generations of students and faculty. Let me see what's my last. So I began this talk by talking about what people want the most. And I said the number one thing that I think people want the most is jobs, and well-paying jobs. And I want to conclude on that note. So there is a raging debate going on in policy circles everywhere as to what is the future of work. What does it look like 15, 20 years from now, if not 5 years from now? And there are two sort of fairly opposing views on this. So on the left is, in case you have never seen it, I would highly encourage you to see it, is a book called The Second Machine Age by a couple of people from MIT, Eric Brynjolfsson and Andrew McAfee, and they paint a really very positive picture that we are on the cusp of major technological revolution that is going to completely transform. So it's called work, progress, and prosperity in a time of brilliant technologies. And the thesis is relatively easy to explain. First machine age, they go back to steam engine. And they make the point that the steam engine and all the sort of developments around that time and since then freed human beings from the limitations of our muscle power. So until then, we were using animals to expand our limitations of our muscle power. But it was very limited. With steam engine and related technologies, we suddenly opened up the use of mechanical power through fuels, fossil fuels for most part, and freed ourselves in a dramatic way. So we had cars, we had airplanes, so mechanical power was no longer a limiting factor for the first machine age. They say the second machine age, due to machine learning and robotics and these types of things, is going to free us from limitations of our mental power, mental limitations. So we are going to get much more capability to assist our brains and minds and do amazing things that we can't even imagine today in the next 25, 30 years. And it's going to create this very bright future. On the right is a paper that also received enormous interest. It is sort of Oxford in 2013. And I'll give you a summary of what they did. So you know our unemployment numbers. They come from Bureau of Labor Statistics. Every Friday of the month, fourth Friday, everybody watches the BLS number. BLS has job categories. I don't know, there are like 100 and some job categories. And for each job category, they describe what is the skill set, what's the work. What Osborne and Frey did is they broke down each job category into skills and work and took pieces and said which part of it is amenable to computerization and automation. And then they compiled all the data into number of jobs, and they came to the conclusion that 47% of US jobs are at risk. That is a scary number. And the question is, what future are we going to have? I think it's probably going to be a mix of the two. So we will have some pain that comes from the right-hand side before we get to the promised land of the left-hand side where all these technologies are going to enable a very bright future. So to end my talk, how can we realize the tremendous promise of engineering to benefit society? I believe that engineering is a huge force for the good for society. How can NSF enable national research and education community to make major advances? And how can we work together with other stakeholders to achieve great outcomes for public at large? With that, I'm going to close and thank you for your attention. Slide 42. Wow, you've been keeping track of numbers. Yeah. A great question. So let me see how I would answer that. If you look at where the money goes, bulk of the money is in research. So if you just divide up my $890 million, bulk of the money is in research. Education and innovation are relatively small fraction of my budget. EHR spends a lot more money on education than so in engineering, education budget is probably $25, $30 million, or maybe a little more than that, but it's not much more than that. EHR is spending $150 million in engineering education. The reason we have it in engineering is because it is the way we can influence what EHR does. And it's a direct connection to the engineering community. Innovation piece, of course, SBIR is federally mandated. So that's 2.5% of NSF budget. So that is federal law. ERCs are largely in research, although they have some translational component. PFI, Eiko, et cetera, are dollar-wise not very large. But the reason we do it is because their impact is so large. So take IUCRC. NSF engineering budget in IUCRC is probably $13, $14 million. The leverage is 10 to 1. 10 to 1 leverage of our, so my 14, not my, NSF's $14 million is bringing $140 million from industry and creating this connection between NSF-funded research and industry. So we see all these as leveraged plays. But even more importantly, I think for NSF and for NSF engineering to continue to make a case to Congress to give us money, if we got rid of these, our case would become much weaker. Much, much weaker. I think you won't believe how much attention and love Eiko gets from policymakers. They just love this idea that NSF is creating something that allows all this basic research to find its way into the real world. Our investment is engineering. It's probably around $15 million. So in the scheme of things, it's significant. I mean, I could take that 15 and put it into fluid mechanics, right? But I think the impact of that 15 million is just incredible. And once we scale it to all other agencies, I think we will be very, very proud of what we have done. So I think that's how I think about this. Clearly, there is not enough money to do all the things that we would like to do. But should I get rid of any of this? I don't think so. But I would love to hear other opinions. Yes? So future is very bright. STCs are not in engineering. STCs are foundation-wide, so let me not. But STCs are continuing. There is a current competition going on. On ERCs, it's on a 2-year cycle. So our last solicitation was 2013. You should expect a solicitation in 2015. This is about the time that we release ERC solicitation. So you should expect that to come out. So I would say the future is no brighter than before, and if anything, I think we are going to continue to do ERCs. The number of ERCs will, as far as the next few years, the numbers will remain the same. Could that change in the future? That's possible. Could it increase? I don't see it decreasing. It could potentially increase depending upon what happens in the future. Because ERCs are our sort of signature large investments, and they do have large payoffs. So again, it's the same kind of trade-off. So ERC is $4 million. So if I get rid of one ERC, I can fund 10 individual investigator grants. That's the trade-off. So we feel like ERCs, on the whole, produce enough to justify that investment into a few ERCs. My current investment is approximately $70 million in ERCs. So again, it's not an overwhelming fraction of the budget, but it's an important fraction of the budget. Yes? For my directorate or for? For ERCs, the metrics of success would be taking a particular sort of somewhat translational engineering research idea. So it's not in very fundamental engineering research, but something that is sort of little closer to translational with a group of companies and create some sort of an engineering advance, technological advance that industry adopts. So that's like the biggest success metric for ERCs. And there are some examples which are really very interesting. So the one that comes to mind right away is our ERC at University of Southern California on retinal implants, where NSF actually funded that research as basic research as an individual PI project, then became an ERC. Then it was funded, they got then NIH money, some DARPA money and industry money, and in 2012, they actually had a device, a retinal implant that was approved by FDA. So that's a success story, right? Here is something that starts with basic research that NSF engineering funds, all the way to something that that anybody can relate to and say, oh yeah, so this led to this implant that can benefit blind people. Yes? Yeah, sure. Sure. Yeah, yeah, yeah. So first of all, I will say that there is a fairly bright yellow line between NSF and NIH as to what NSF funds and what NIH will fund on medicine. At NSF, the biology directorate funds only basic biology. They pretty much stay away from human disease. So that's really not their main thing. Engineering directorate, computer science directorate, even social and behavioral economic sciences directorates, we get much closer to disease and health. Engineering funds a lot of the basic research on biomedical technologies, biomedical engineering, like this advanced cellular manufacturing, right? So this is not really ready for NIH or FDA investment at this point. So NSF will do the basic research. Another great example is optogenetics. Optogenetics was funded by NSF. It's a huge advance in biomedical sciences. So our role we see is basic research that is not ready for NIH investment yet, but it has to have some grounding in our case, fundamental engineering, fundamental biomedical engineering. Is that helpful? Yeah. Anything that even gets close to the trials, we are out of it, and we are not even going to go close to it. And we like, so just another example that we just recently did in terms of collaboration is, 3D additive manufacturing is something that NSF started, and tissue engineering is another thing that NSF started. So there is a lot of interest. In fact, there is a company in San Diego called Organovo that uses 3D printing to print organs on a. So we just had a workshop with NIH on a vision for tumors. So can we use 3D printing type of technology for printing tumors that will have all the properties of a tumor in our body, but could be used for drug testing and drug development and so forth. And so the idea is take very high high fidelity images, use 3D printing, and create this thing with the vasculatures and all the stuff that is. So that was a joint workshop between NSF and NCI, NSF Engineering and NCI, and a report is not yet there, but it will come out at some point. And then we might figure out a role for NSF engineering in basic engineering research that needs to happen for this to happen. And then at some point, NCI will take over. So that's the kind of thing that we try to do between NSF and